So, welcome back student. We are going to start today's session. It is module 3, lecture 1, satellite communication, MECE-106A. Shongita Roy, assistant professor, electronics and communication engineering department, Narula Institute of Technology. Today's content is satellite subsystems, and under this today's topic is communication, telemetry, ranging and control. We will start this session, and this total topic is divided into two parts in two lectures. So we will start this session and see how much we can proceed, and in the next day we will conclude that. A communication satellite incorporates various subsystems whose function in principle are distinct. It is customary to distinguish the communication payload or communication modules, antennas and repeater from the platform or service module that supports and powers the payload. The organization of a communication satellite platform is determined mainly by the following. So before going to this, we must say this is the part of the only satellite. We are not concerning any earth portion here, means earth station we are not considering, only the satellite that is in the space. So the following are the points which is requiring the organization of a communication satellite platform. The requirement of the communication payload, the nature and effect of the space environment, the performance of launchers and the constraints which they impose. These are the points which should be taken into consideration. So this is the concept of a spacecraft, how it is, that is to satellite, our concern. So these are the antenna module. This is 3-floor or 3-tier repeater module. These are the antennas. Therefore, antenna are in the antenna module also, or a part, as well as it is a part of the repeater module also. Then there is service module. Subsystems. The function of subsystems to be provided and the most significant characteristics are indicated in the table follows. 3 common characteristics are not indicated but are essential and should be emphasized. That is to minimum mass, minimum consumption and high reliability. Because satellites are in the space, so we cannot go there very frequently. No one will go, no one will supply anything to there. Therefore the module should be indigenous. So in the subsystems, the list of the platform subsystems that are inbuilt there, they are attitude orbit control, AOCS. Its main function is attitude stabilization, orbit determination. Characteristics is very high accuracy should be maintained, otherwise system may collapse at any time or it may not perform at all. Propulsion, provision of velocity increments, specific impulse mass of propellant. Electric power supply, provision of electrical energy, power and voltage stability. Telemetry tracking and command, TTC, exchange of housekeeping information, number of channels, security of communications. Thermal control, temperature maintenance, dissipation capability. Structure, equipment support, rigidity and lightness. Therefore, system should be very strong. At the same time, it should be light in weight. Now we are concerning, or we are taking this information from the reference 2, which is given at the end of this session, and from that book it is page number 580. We are taking from there, and today onwards we will give the page number from where we are taking this, and the book is Satellite Communication Systems, Techniques and Technologies, and the details of this book is given in the reference 2. So telemetry tracking and command TTC and onboard data handling OBDH. It provides receiving control signals from the ground to initiate maneuvers and to change the state or mode of operation of equipment. Telemetry tracking and command deals with this, as well as transmitting result of measurements, information concerning satellite operation, the operation of equipment and verification of execution of the commands to the ground, enabling measurement of the ground satellite distance and possibly the radial velocity in order to permit location of the satellite and determination of orbit parameters. Now the frequency used. The TTC link should nominally be operated with the space operation services frequency bands. The frequency normally used are in the S band as follows. For uplink it is 2025 to 2120 MHz. For downlink it is 2200 to 2300 MHz. It may change depending on the frequency it is used. It may be K, may be Ku band or higher. The telecommand links. The telecommand links TC are provided by a carrier whose frequency depend on the band used and is phase or frequency modulated by a subcarrier at a few kilohertz or 8 kilohertz. Digital phase modulation of the subcarrier by the data has previously been released. The bit stream, often NRZL formatted, has a data rate ranging from some hundreds of bits per second to several kilobits per second depending on the application. On account of the low bit rate, the use of a subcarrier enables the useful spectrum to be separated from the carrier itself. Commands depending on the particular mode selected can be executed immediately after reception, stored in memory and executed on reception of a specific command, stored in memory and executed when activated at a given time determined by the time management system on board the satellite or when activated by a signal produced by one of the systems on board the satellite. So this is the block diagram of TTC subsystem. So this is mode selection and interface unit. It is timing control decoder. It is encoder. It is the radio frequency in the form of gigahertz. It is coming. Therefore, it is from the outer space or from Earth station. It is coming. Then it is down to intermediate frequency from gigahertz to kilohertz. Then to the original baseband signal. Therefore, there is omnidirectional antenna that is receiving the signal. Then duplexer are there, two duplexer are there. This is TC receiver, this is TM transmitter. So this is nothing but receiver, transmitter, receiver, transmitter. So this mode selection switch, whether it is transmitting or receiving. So there is a communication payload is there. Therefore, there is an analyzer also there, multiplexer is there. Therefore, it is encoding, it is decoding. When the signal is coming, it is decoding, and when the signal has to send, it will be encoded. So it is data and it is also data. This is for transmitting, it is for receiving data. So this is all about this block diagram of the centralized TTC system. So telemetry links. The telemetry links are also provided by a carrier which is in phase or frequency modulated by a carrier at a few kilohertz, 40.96 kilohertz. The digital data phase modulates this subcarrier. The data rate ranges from a few kilotens of bits to few kilobits per second. Data are obtained in either of the following ways: directly from satellite equipment and conditioned analog to digital conversion and then formatting, and the related steps are there in the telemetry encoded at the output of a processing unit on a local onboard network to which the various satellite equipment has access. Telecommand and telemetry message format standards. There is a need of message format standards in order to ensure compatibility of the satellite telecommand, decoding and telemetry encoding systems which the control ground station and the ground data handling and processing systems. In addition, a standard common to the various space agencies and satellite operators allows a given party to operate their satellite using the facilities of another body if required. Finally, the purpose of a standard is to unify data interfaces and data handling operation in ground systems. Two main types of standard have been elaborated. The PCM standards were published in the 1970s and as an example defined by ESA. It is some standards are there. In this book they are talking about particular standard. There are a lot of standards are there, no problem about this. The packet standards originated from the recommendations of the Consultative Committee for Space Data System and are available in a series of reports. PCM standards. Telecommand. The telecommand message is organized in frames processed by a group of bits for acquisition of synchronization. Each frame consists of words of several bits. The length of the frame depends on the applied standard. For example, in the ESA standard, the frame consists of 96 bits. The first word of 16 bits constitutes an address and synchronization word specific to the destination decoder. It is followed by a mode selection word for 4 bits, which are immediately repeated. So this is a command message standard how it is. Address and synchronization word bit, this is 16 bit, mode selection 4 bit, mode selection repeated again 4 bit, first data word 12 bit, first data word repeated again 12 bit, second data word 12 bit, second data word repeated 12 bit, third data word 12 bit and the repeated one also 12 bit. This is a typical message total packet how it is sent. Telemetry. The telemetry message is organized in frames and a group of frames constitute a format. Each frame consists of words and start with a synchronization code. It is just like a TCP/IP protocol how the information sent like this. There should be some frame and within that particular structure the information will receive as well as transmit. In the ESA standard, the format consists of 16 frames and each frame consists of 48 words. The 8-bit word constitute the data. This might be a part of a data word for data whose resolution requires coding in more than 8 bits, or a block of data which requires only a single bit such as state of a relay. Now packet standards. The Consultative Committee for Space Data Systems (CCSDS) is an international organization. Its members are the various national space agencies around the world. From the beginning of the 1980s, CCSDS developed a series of technical recommendations for the standardization of the common data system function. Telecommand. The introduction of the more capable microprocessor-based spacecraft subsystems result in an increase in spacecraft autonomy and complexity requiring data systems with high throughput needs. Common requirements for greater telecommand capability and efficiency with reduced cost are addressed by the CCSDS telecommand concept. The proposed layer structure allows a complex spacecraft commanding procedure to be decomposed into a set of simple functions. With each layer, the function exchange information using standard data formatting technique and standard protocols. Three main data formats are defined. User data packets, TC packets, the TC transfer frame to reliably transport TC packets, the telecommand link transmission unit which encapsulates the channel coder transfer frames. So this is a telecommand data structure. This is the header, then data used, and this will be consecutively going on. Then segmentation layer, frame construction, code block construction, command link transmission unit construction. So it is a step-by-step procedure. Packet telemetry is a concept which facilitates the transmission of space-acquired data from sources to ground user in a standardized and highly automated manner. Packet telemetry has a layer structure where each layer implements the difference function to allow the multiplexing of various kinds of telemetry data onto a single physical radio frequency channel. Two main data structures are defined in a packet telemetry. The source packet encapsulates the data. It will be shown in the next figure, which may include ancillary data and which may be directly interpreted by the ground user processor. The source packet header contains an identifier used to route the packet to its destination sink and also information about the length, sequence and other characteristics of the packet. The transfer frame has a fixed length for a given mission or satellite, and it embeds the source packet to provide reliable and error control transfer through a transmission media. Error control also always there like TCP/IP OSI model. The transfer frame header permits the ground system to route the source packets to their intended destination. So this is the telemetry source packet, the packet header, then packet data. This is the data, but see, the header is larger than the actual data because actual data is limited. Corresponding shielding or protection should be very high. Virtual channelization is used in the multiplexing mechanism that allows various sources which generate packets to be given virtually exclusive access to a physical channel by assigning them transmission capacity on a frame-by-frame basis. So a virtual channel is a given sequence of transfer frames which are assigned a common identification code, enabling unique identification of all transfer frames belonging to that sequence. The next figure illustrates the overall telemetry data flow through this layer packet telemetry structure. So this is the overall how the packet is passed. So this is the physical channel in between radio link. Therefore, one is earth station, another is the satellite station. So they are the different sinks or processors are there, source packet, and this is another source to destination it is going. So from here it is coming and up to there. Say if it is a ground, then the ground station will finally process the data which is coming from the satellite and vice versa. So the source is generating the packet and the multiplexing packets, and it is going through the master channel and then through the physical channel to the the air, atmosphere are there. Finally again it is going, reverse process is there, the receiving signal is through there. Then here it is multiplexing, the reverse process will be there, demultiplexing. Then it is again processed and finally the signal carrier will be isolated and the baseband will be taken from there. Onboard data handling, OBDH. Onboard data handling deals with command processing, decoding, validation, acknowledgement and execution, immediate or deferred of the command signal, acquisition, compression, coding, formatting of telemetry information, processing of data relating to the onboard management subsystem itself, such as time, configuration, and on demand from the satellite subsystems. Onboard data handling continued. It is of strong storage of data, telemetry data, modes and software, synchronization, data timing and traffic management, onboard time management, distribution of onboard timing and clock signals to subsystems, dating of events and measurement, management of traffic between subsystems. 6. Monitoring and control, acquisition of analysis of monitored and diagnostic parameters, decision taking, that is to changing into survival mode and configuration, generation and execution of appropriate commands. So it is the adaptation of the internet protocol to satellite communication. So this is the satellite and this is the base station. So from base station, info telecommand will be going to the satellite, and from satellite telemetry will come, and here different information is processed. Then it is going through the data link. It is nothing but the OSI model. So it is through space. It is going to the same process data link and physical layer, and going through network layer and corresponding different layers, and corresponding work is processed over there. It is nothing but TCP/IP model. OSI 7 models are showing, but nowadays it is TCP/IP model they are following. Now this model we have already discussed in the initial slides. The centralized architecture. The onboard data handling can be restricted to decoding telecommand signals and encoding telemetry signals. The interfaces with this equipment consist of a subcarrier modulated by a bit stream from or to the respective radio frequency equipment, and the telecommand and telemetry signals to and from the satellite equipment on as many links as there are signals. The block diagram of this architecture is given earlier. Again, we are showing over there. Modulator architecture. The system organization uses a decentralized architecture with a communication bus between the various pieces of data processing and handling equipment, and this is shown by this figure, modular architecture for data management. So this is the central unit, terminal unit, subcarrier, and this is for, this is the signal is coming, receiving signal, so the carrier it is decoded and going to the direct to the channel, and it is the subcarrier, it is going out. So this is for transmission and this is for reception. So the TM channels and TC channels. So remote terminal unit, it is the user terminal unit. So in between this path will be created and they will be interfaced between these two. Data bus interface and protocols. In order to allow the use of standardized equipment, the interfaces between the units and the communication protocol have been the subject of standardization. Two main standards are used for the local housekeeping data network on board a communication satellite. The ESA onboard data handling OBDH and standard US MIL STD 1553B standard. Satellite control. Satellite control operators consist in some cases of elaborating command in order to execute actions in accordance with information available on board the satellite. With the rudimentary onboard management architecture of first generation satellite, the information from telemetry channel is grouped into control station where the context is analyzed and the decision taken and transmitted on the telecommand channels. This mode of operation is quite suitable for generation geostationary communication satellite, which are continuously visible from the control station and whose management is simply, they have few TTC control. Tracking. Measurement of radial velocity. So we will now start measurement of radial velocity. So wait. So radial velocity can be obtained by measurement of Doppler effect. It is necessary to ensure frequency and phase coherence at the transparency between transponder between the downlink and uplink carriers. So according to Doppler effect, this is the measurement. So thermal control and structure. The purpose of the thermal control is to maintain the satellite equipment with the temperature ranges which enable it to operate satisfactorily by providing its normal performance and avoiding any irreversible deterioration when it is not responding. This also applies to the structure of the satellite, which must remain within a mean temperature range in order to minimize deformation and guarantee precise alignment of attitude stabilization sensors and antenna. Thermal control specification. Thermal control must be optimized with respect to the constraint of both the operational and transfer phases. These constraints are very different. So today we have the idea how the satellite on board it is operated, the telemetry and the different communication signal from ground to satellite and satellite to ground, and these are basically the OSI 7 layers that is integrated to TCP/IP control. Over that it is operated, and the different type of modulation schemes are utilized, both digital as well as analog, but mostly today's are digital communication. And in this communication, very accuracy is maintained very precisely. Timing synchronization is very important because satellite is very far from Earth. Distance create lot of problems. So precision is very important. High quality sensors are there. So for today we are just going up to this. We are ending the session. In the next day we will study more. So up to this, these are the references, and we are concluding the session. Thank you. And in the next day, we will again start. We will start from the beginning little bit, and then we will continue the session. Until then, we are ending the session over there.